Hello, Calculus 1, welcome back. We were in section 5.7. We were dealing with a lot with this integral, 1 over u du, a lot of u substitution, but then in 5.7 they particularly kind of show you this. So a lot of u substitution involves the denominator. This one could be like that, but there's a little twist on this one. I want to teach you this. Anytime the numerator is a higher degree, so the numerator is an x squared, that's degree 2. The denominator is just a linear function, so it's degree 1. So when the numerator is a higher or equal to degree, greater or equal to degree, you ought to perform good old long division. You ought to, before you integrate, you ought to do long division. It's sort of like an improper fraction, and you should make it proper by doing long division. So, some people hate long division. I kind of like it. I'll remind you how to do it. I'm going to take x minus 3 and divide it into 2x squared minus x plus 4. I want to do this long division. I'll change the integrand if I can do this. So here's how you do it. You focus on the x and you say, how many times does x go into 2x squared? And the answer is, what do you multiply by x to get 2x squared? And the answer is 2x. So that's a 2x squared. You multiply. Now you multiply that also. That's a negative 6. And if you remember division, good old long division, you now subtract. So I subtract and I subtract. Subtracting this will be gone. Subtracting a negative is actually adding, so I guess that's 5x. You can bring down the 4, and now you divide again. Does x go into 5x? Yes, it goes positive 5 times, because 5 times x is 5x, and 5 times the negative 3 is negative 15. And now you subtract. Subtract, subtract. Subtracting those is gone. Subtracting a negative 15 is actually adding, so this is a 19. Does x go into 19? No, it doesn't go into 19. That's your remainder. And maybe you remember that you write your remainder over your divisor. So, what was this division problem, this integrand here, we were trying to integrate this. We did the long division, and that quotient is that answer right above there. So we've transformed this integral into this integral, 2x plus 5 plus 19 over x minus 3 dx. And this is really easy now. Can anybody integrate an 2x? Yeah, it's a power rule. You add 1, you get x squared, you divide by 2, I guess you get x squared. X squared divided by 2, yeah. Can anybody integrate a 5? Yeah, good job. Can you integrate this? Yes. Technically, you need a little u substitution on the denominator. I'm going to do it in my head. If you let u equal the denominator, du is dx. Nothing interesting happens. It's a 1 over u du. No 1/3 gets spit out. Nothing interesting. So it's just a natural log of x minus 3. Now there is a 19 out in front of that. A positive 19 natural log of x minus 3. So we integrate, integrate, integrate. We're done. That was cool. But we needed that long division. We needed that long division. Here's another one. Let me show you another one. I'm going to violate my rule here, actually. Watch this. 4x plus 1 over x plus 2. So I just got done saying, anytime the numerator is a higher or equal to degree, you should do long division. This would be real short long division. You could do it. It is easy. It might be the best way to do it. But there is another way that you didn't want to do on this problem. This was better to do long division. But there is another way. You know what, if you didn't think of the long division and you just let u equal the denominator, you think, I'll let u equal the denominator, du is the derivative dx. Uh-oh, here I go. I try to replace this stuff. The denominator's a u, the dx turned into a du, right. But, this is a little dangerous. I warned you about this before. We have this 4x plus 1, and we can't have x's mixed with u's. You can't pull variables x out, but I did warn you that you could solve for x in terms of u. So x is u minus 2 if you move the 2 over, and I could replace that right there. So what does this turn into now? U minus 2, the x is a u minus 2 plus 1 all over a u. And because, I mean, in a way, you're still going to do some division here. Actually, let's distribute and clean that up. That's a 4u minus 8, but when you add the 1, it's a 4u minus 7, I guess, all over u. And you still have a higher degree than the denominator, an equal to degree than the denominator. And you might think of long division, but you don't need long division. You just kind of need short division. In fact, they had a lot of these problems in section 5.1 where you actually just divided this single term into both of these. Or you split up the numerator, or you do it like this. That's a 4u over u, so that's a 4. And then that's a 7 over u. So we just kind of split up the numerator like that. Anyway, here we go. Can we finally integrate? Yes, getting rid of this. And I sort of did it without long division, although you might call that step a little short long division. But I split up the numerator is what I call it. But here we go. Can you integrate the 4? 4u. Can you integrate the negative 7 natural log of u? And the problem's over except for one thing. We should put our u's back. What was it? Our u was x plus 2. 4x plus 2 minus 7 natural log of x plus 2 plus c. All right, that was fun. One little added twist I want to show you on this problem. This problem was in the book, and if you look this problem up in the back of the book, they might have this answer. Which is almost the same. What they don't have is the x plus 2. And let me explain what they did. So there's nothing wrong with my answer, but you could do this one more step. If you distributed the 4, you'd have a 4x plus 8. There's nothing wrong with leaving it like that. But when you have a plus 8, and later down here you have this arbitrary c, which is an arbitrary constant, well, can't you just add the 8 into the c? Let the arbitrary constant c absorb that constant 8, and write your answer like this. I mean, it's a different c than it was, but it's just as arbitrary as it was before. So they do that. We do some funny things sometimes with that arbitrary c. It's an important part of indefinite integration. Okay, I'm still in 5.7. I'm going to get rid of this problem. I want to show you what else is in 5.7 quickly. What else happens in 5.7 is all of a sudden, because we've got this rule, we kind of learned this rule, we can integrate the rest of the trig functions. So all of a sudden we can now integrate the tangent of x dx, or the tangent of u, sorry. Yeah, let me just write it as a rule like this. I can write the rule with x, or I can write the rule with u. It's the same rule. We can do that now. And the answer is the negative natural log of cosine u plus c. And I think I'd memorize that if I was you. It's not difficult to do, though. Let me just show you how to do it. If you know from trig that you could rewrite tangent as sine over cosine. Now again, look at me, I'm using u's. So now I want to do a u substitution. It's kind of funny when I do a u substitution and the variable u is already there. I should use a different letter. I think I'll use w. So I'm going to do a w substitution. I'm going to let w equal the denominator, cosine u. What's the derivative? I need dw, the derivative. The derivative of cosine is negative sine u du. Oh man, that makes me happy. I got a w in the denominator. This is an integral. This is an integral. I got a w in the denominator, and look at that numerator. Sine u du is my dw. It's off by a negative sign. You know, I move the negative sign over here. In fact, I'll just put it out front. Negative dw over w, which is this rule. 1 over u du, 1 over w dw. The answer is negative natural log of w plus c. And what was w? The cosine of u. So I don't know what I would memorize. I think I'd memorize that that's the integral of tangent. You never could integrate tangent before. Tangent is not somebody's famous derivative. Hang on, who could you integrate? You could integrate secant squared. Secant squared is a famous derivative of tangent. So when you integrate a secant squared, you get tangent. But tangent never seemed to be somebody's famous derivative, so we never knew the answer to tangent, but we figured it out with a little sine over cosine, do a little u substitution on the denominator, and you get there. But again, you could go through that procedure or you could memorize that. Another one. Well, actually, a couple thoughts here. Got several thoughts here. One is, if you took that -1 using log properties and moved a -1 up there, all of a sudden you have the natural log of the cosine function to the -1 power. That's not cosine inverse. Don't make that mistake. That's to the -1 power, which means 1 over cosine, and that happens to be the reciprocal of cosine, which happens to be secant. So some people write this rule like this. The answer to the integral of tangent is the natural log of secant. Or I've memorized it as the negative natural log of cosine. But they're the same thing. I just proved that to you. Using log properties, that negative can move up as a power. That power can change cosine into a secant. Similarly, what about, I'm going to use x. What about the cotangent of x dx? It is, what is it? I think I got it memorized, but I would do the same kind of procedure. I'd write cotangent as cosine over sine. So I guess I would get this. I don't think it doesn't have a negative sign. Natural log of sine x plus c. Here's one. What about the integral of secant? We never could integrate secant. We did secant squared. Remember, he was a famous derivative, but we never could integrate a secant. And the procedure, there's a little trick to it. I don't even care to tell you what it is. Here's the answer. There's a little trick to getting here. Maybe you care, maybe you want to know. If you're dying to know, let me know and I'll explain it to you. Or maybe you can look in the book. Here's one more. Cosecant. Negative natural log of cosecant x plus cotangent x. So we now know how to do all the trig functions. I mean, earlier in this chapter we could integrate sine and cosine. And we could integrate famous derivatives of trig functions like secant squared or secant tangent. But we never could integrate a tangent or a cotangent or a secant or a cosecant, but now you can. And they all involve natural log. So maybe we memorize these. I tend not to ask about cotangents or cosecants too often. This secant comes up and this tangent comes up occasionally. So we tend to memorize these or use these. I want to add one more thing for them. I'm kind of finished with 5-7, but I want to add something else here. What if, you should know this of course, what if I'm integrating then a secant of 3x? Well, here's your new rule. Hey, when you got a secant of x, that's the natural log of secant x plus tangent x plus c. Okay, that's the new rule for secant. Well, what if it's a secant 3x? I hope you know that you should do a little u substitution on the 3x. The result of that u substitution on the 3x is it spits out a 1/3. So without me even writing that, here's the answer. It's 1/3 natural log of secant of 3x plus tangent of 3x. It's that rule. It's that rule. But if it's a 3x, you do a little u substitution, and the result is it spits out a 1/3. Maybe you've done enough problems to understand that. If you haven't, check out some of the other videos. That's what happens. Or do it. Let u equal 3x. du is 3 dx. Replace that with a u. Replace the dx with a 1/3 du. And it spits out a 1/3. Right. Okay, good luck. Good luck.